Welcome, Frank Soboczenki. We are so excited to talk with you a little bit today. Tell us a little bit for our listeners who haven't met you yet, what it is that you do and how you have come to be involved in space.
Hi there. Thank you very much for having me. So I'm an assistant professor at the University of York. I'm also a affiliate computer scientist at King's College and Northeastern University, so I wear a couple of different hats. I love science and I enjoy working in challenging problems. And over the years, I've got to be very close with NASA and some activities there. So it all started, I think, with the first or the second Space Apps call that they did. So Space Apps is a worldwide hackathon, and I think at the time when I was involved, it was the largest in the world. And I was hosting that over 5 years here with a team in York, in the UK. And we won it in 2016 and got invited to Kennedy for a week and to attend the OSIRIS-REx launch. I believe this is due to come back now, actually. It's the sample return mission to an asteroid called Bennu. And and that just jumps things. So since then, I've been getting into more and more people and more projects. So.
Right. So I want to make sure we had a little audio blip there. I want to make sure you competed and were a part of OSIRIS-REx mission, correct?
I didn't compete. So and NASA kind of some challenges that everybody is work on over this weekend. And would then the first the global prize, a global nomination by NASA and its partners. And if you win that, you get invited to attend the launch at Kennedy Space Center. So that's what our team got in 2016.
I think we're having a couple of technical difficulties. Are you experiencing it on your end too? Are we freezing up for you every now and then?
No, I think it's all right.
Okay, so we heard that you went. All we got from that was that you were in the competition. I think we understand that it was for a mission that's going to be returning soon. I hate to ask you again. Would you just share that one more time with us? Because now it seems to be a good connection, and we'll just kind of edit out the others.
I'm sorry, Frank. It's a little. It went in and out, the audio, and your video would freeze momentarily. I don't know how to fix it at our end. And
but it seems okay now. So we'll edit out that first part.
We're just gonna cut out the first part.
Okay, no problem.
I think we heard really well. You're at the University of York and you have other appointments at King's College and Northeastern University. It was after that it got wonky.
Competition.
Yeah, it's not a competition, but it's a little wonky. Could you start with after you did your educational connections and you said you had done some stuff with NASA? Right about then, we will just cut out this little part and pick it up.
Sure.
This answer.
Sure. Yeah, no problem. So while during my studies, I got involved with NASA on different things, and one of them was the NASA Space Apps Challenge, which is a global hackathon that is at the time was the largest in the world. It happens every year, and we participated in this competition and then won it in 2016, and our team got invited to attend the OSIRIS-REx launch. This is a sample return mission, and this mission is just, I think, due to return. Actually, there's a little spacecraft that went to an asteroid, and it kind of scraped something off that asteroid, and it brings this sample back to Earth.
Yes, that's at least what, 300 million miles one way to the asteroid?
I think so. Yeah, it's quite a journey. Yes. Right. So since then, I got involved in like different things with NASA, and the next thing that someone sent me an email. Are you interested in? At the time, they were running something called a NASA Frontier Development Lab. I think it's still running to date, and I participated in this in 2018 at Ames Research Center. And this is a program where it's like kind of an accelerator. So research scientists are invited to tackle some of NASA's toughest problems with machine learning and AI at that time. And they have different topics and different teams, and each team is kind of structured into 4 scientists and 2 kind of lead scientists, more like the advisors. And the 4 scientists are each either 2 subject scientists and then 2 AI or computer scientist specialists, depending on the challenge. And yeah, lots of stuff happened then there.
That's fantastic. I noticed in doing a little bit of research about you, you were involved with Gene Lab and artificial intelligence as it relates to Gene Lab. So I'm in a previous, life, I'm a biochemist that's now involved with education and CubeSats, but I'm really interested in Gene Lab and how you applied your expertise to Gene Lab. And could you share a little bit about that mission with our audience?
Sure, happy to. So one of those projects over the years with the FDL program that I mentioned was about astronaut health. And that brought together some scientists from Gene Lab and some computer scientists and AI researchers. And the first one we tackled was they were interested in having an AI model that can help identify causal reasons for cancer progression. So to model cancer progression more effectively, and specifically in a context of space radiation, because NASA is interested what effect, what environmental effect the radiation up there has on the human body, and it's quite hazardous and quite tedious up there, as you may know. So they were interested in looking at a specific cancer tumor data, and we were tasked to come up with a machine learning tool framework that kind of helps. Hey, yeah, here's a tumor data, and it highlights some causal reasons for this tumor to develop. So this was also together with Mayo Clinic. You may know that. And they gave us the world's largest colorectal cancer data set. Now, when I say the world largest, how much data points do you think that is? So usually machine learning needs a lot of data, like, I don't know, hundreds and thousands of data points for specific machine learning models to train well. How much do you think, how large this data set was?
I'm based on the way you set it up, I'm either going to say 100 or a billion. I don't know which way to go. So we're going to go really small set of numbers.
Well, I'm thinking people
really
who participate in colorectal
well,
in general is going to be slow.
So it depends on if one patient is a data point or you have 1,000 data points within a patient. Oh,
well, no, one patient is one data point. Yeah.
1,000 patients. How many do you have?
I wished it would have been the case, but no, it was 100 data points.
Yeah, people don't want to take the poop.
It's a
shame. Exactly. Yes, exactly.
It's a shame because, we're capable of gathering so much data on any patient, right? With non-invasive techniques, you would think that any research project that's being funded, you would be able to amass more data than you could analyze, right? That's the problem. Isn't that what you do? Your expertise is you can take very, very large data sets and have the computers or your algorithms process the data more rapidly than maybe we've been able to in the past. Is that one of your happy places?
Yes, I would say that's the case. For that particular project, though, with those little data points, there's also a subfield in artificial intelligence that actually focuses on specifically that and tries to apply techniques to get the highest accuracy for the lowest data points, how much we can get out of there, basically. It's also related to zero-shot learning. So you have like one shot to kind of get as much as you can get.
Oh, wow, that's very cool. My question, I have lots of questions now, if it's okay.
It's okay.
Second, do your algorithms allow that if you have a small number of data points that somehow the machine learning can extrapolate even within a single data point to gain knowledge, maybe a little bit on the left or right of whatever graph you're looking at, even though it's a single data point, and help me understand how that impacts things like your confidence in a result, or like, the confidence that you might have in something that your algorithm spits out?
Yeah, that's a very good question. I think this very much depends on what the low data points are. I think for a single data point, it's very hard to say, and it's hard to extrapolate anything from a single data point. But from a low data point set, like 150 or 100 or so, you can get some early quick prototypes. And usually in machine learning, this is done not to analyze the data, but more or less to check if everything else is okay. So you have like a pipeline set up, and you just pump a little data set through and see what's going on. But for low data points, there are certain techniques, and you have to be very careful about how you analyze this, also with confidence levels, as you indicated that. For this particular project that I highlighted, we developed a platform that utilizes 3 causal inference methods that were already well developed and are currently discussed in the research community. But we just provided them with a way to easily use it and to apply different data sets for this, and to also have a very user-friendly interface. This is another big topic currently in AI, like explainable AI, so that the experts or the layperson kind of really understand what's going on in a very easy way. And in this case, it was for clinicians, not only for the gene lab people.
Right
there.
So following up along this line, you mentioned one type of cancer data. In my mind, I'm wondering things like in the eyes or the brain. Other types of cancer, part 1. Part 2 of this is, was the data centered around ionizing radiation, like particles, or was it only like X-ray, UV, X-ray, gamma ray? Were you looking at pure EM radiation? Were you looking at highly, high energetic particles with lots of velocity? What was the root cause of the cancer because of the space environment aspect, or were you just looking at the patient's data that you had and sort of extrapolating the life cycle of that cancer?
A very good question. I'm unsure about what kind of radiation it was at the moment. I would need to check, but I believe we looked at the data option, as you said, and looked at how much we can extrapolate from there. But I believe there was also gamma radiation involved. I may be wrong, but I would need to double check this. And that was just the first project. So then the next year, now NASA Ames and Gene Lab was interested in cooperation with Intel and Google to kind of use this tool now, but more effectively, in terms of, there's all these problems with those data sets that we just discussed. And we have data at Mayo, we have data at NASA, we have data at other locations. So they were interested in us utilizing a certain subfield from AI that's called federated learning. So what this means is you have your machine learning algorithm is not taking the data from different locations. It takes the models. What that means is you have the data sets never leave where they are. So this is particularly interesting for all the healthcare providers because of all this, privacy and everything. So you don't want to share patient data. So the data is encoded where it is, and then it is ready for machine learning ingestion, and the models would run locally at Mayo or at NASA, or wherever this is part of this specific network. And then only the weights, only the models trained on this encoded data sets are shared, fused together in one cycle, trained on, and then the results of the models the updated models are shared back to all the different locations until the next cycle happens, and so forth and so forth. So you never share the data sets. And we did this, we used the previous platform and enabled now a federated learning mechanism. And NASA is so interested with that. So they use it now, I think, to establish well, it's already in a run, on the run in Johnson Space Center. And I think also it's running on the space station as well. It's due to be involved as a data location point. So we have NASA, Johnson Space Center, Mayo Clinic, and Intel, and the ISS, and a couple of, I'm not sure how many locations they have involved. But on the ISS, there's a computer. There are 2 GPUs up there, so you can access this from the ground. and you can run some machine learning models on the ISS and then use it as one of those locations. Now it's a bit more exotic because you have a line of sight disconnections sometimes when it may not have all the time clear data transfer, but this just adds to the resilience of this system that the system has to come up with.
So I'm not as techie as Kevin. And so speaking on behalf of some of our listeners who might not be as clear, when you're talking about AI here and the use of the experiments that you're doing, are we suggesting that you're doing experiments on AI itself or using the AI to extrapolate or get the data? So can you help me understand a little bit more about how are you using AI or are you testing AI? I guess is where I need to catch up a little bit.
Yeah, no, that's great. So in this particular use case that I just described, we're using a different form of AI to analyze the data. So we want to use the AI to analyze again using these causal inference methods to analyze the cancer data, but we don't want to share the data. We want to keep the data where it is. So this specific AI is like an umbrella network, and this umbrella kind of ties into each of those different locations, and it encodes it on one location, and then it got shared back to a central server kind of. And the ISS is one of those different nodes in those networks, basically.
So essentially, it's ostensibly making it easier and faster to analyze the data from a different perspective that you might not otherwise see.
That's a very good comment. I would say I need to be careful. So easier in terms of how easy you can get to the data, I would say yes, because it doesn't require a lot of the authorization mechanisms that maybe are involved.
You're not in HIPAA violations, right?
Yes.
You're not in HIPAA violations. And what I heard, and please correct me, this is way beyond anonymized patient data where you get anonymized data. You're never removing the data. You send, it's like decentralized learning. You send some elements, some software out to a remote location where its analysis is done, and you only get sort of results of interest from your analysis on site. Is that reasonable?
Yes. So we only get the weights back, and the data may still be anonymized. So there may still be some local security mechanisms involved, because all we need is just the data. We don't need the person, the names, and any of this. Exactly. So we just need to really,
And I want to make sure that's called federated learning. Federated learning.
Okay, so now I can see why that is that there's a draw there, because that removes some of the obstacles that you might otherwise have, so it can be faster in that respect. And
frankly, if you get more institutions to partner with you, you get more and more data to make your model even more smart, more intelligent.
Are people reluctant to use it though? Just because I know just like we were talking about the reluctance with the colorectal people, right? Like, is there's still like that uncertainty factor related to whether or not it's trustworthy, or are people still scared of AI to the point where it's not been readily accepted yet?
Do you mean the people who
like the ones who would
too, or?
Yeah, sorry? I mean, even the groups that you're working with. So like the idea that you're collecting data, and yes, it's going through this kind of like anonymized machinery. I'm going to say anonymized, right? But is there still like this kind of misunderstanding around whether or not it's safe? And by that, I mean like the collection of data.
Yeah.
So I would need to distinguish here, separate here I would say that the general audience in terms of everybody. I think there's still a lot of fear that some of those mechanisms may cause some adverse things, and there may well be. So, the research program scientists and also the medical scientists that were involved in this project, they all were very happy. They all were very keen and enthusiastic to utilize these new machine learning methods to basically get better insights, to get new pieces of knowledge that add to this very difficult research topic of cancer progression modeling. But I would say, so we need to distinguish this here. And the patients themselves were not really involved in that part. So they may have given the data and may have signed a consent form at some point, maybe even a year before this idea even came around, but that they agreed that their data would be shared, used for some form of research project in the future. And we were just happened to be around the corner that we're able to use this data set. Yeah.
Thank you.
I'm ready to pivot to deep space. Can we do that?
Yeah, sure.
All right. How does this type of machine learning and AI that is your happy place, how does that relate to, let's say, autonomous probes or autonomous exploration? What do you see as the biggest non-medical uses for something like federated learning? Or is that really, do you have an application for that relates to how we might better explore Mars or, even beyond?
Yeah. So lucky, I'm very lucky that this podcast lasts for 5 hours now, and I can just carry on with projects, right? So there are multiple applications out there. So this ranges from spacecraft telemetry monitoring to communication networks. So even CubeSats or small satellites that can be deployed to assist with communication, and machine learning on board for processing the data for various tasks, to navigating, to even monitoring astronauts for their health. One of my recent projects was flying a CubeSat mission, and we were tasked there to validate very new state-of-the-art technologies that goes beyond even the current machine learning standards. So there we go into the world of quantum machine learning. So that's one step further where research scientists try to integrate quantum theoretical mechanisms from quantum physics into machine learning algorithms to just apply and see if some of these concepts can be realized. And we were tasked so NASA was interested in this, and we were tasked to fly a test CubeSat with that. We had we packed all sorts of sensors in there, but we had 2 compute units on board, and we have basically 2 mission goals. One was to demonstrate that this thing can be used during flight, and the second one was to demonstrate that because it's working, we can process the data on board and therefore only need to download the results. So that kind of was a big interest of NASA as well, because any kind of form of communication, the further out it goes, the more expensive it is, and both in computation and in cost. So if you cut down the data streams to like only little important things, then that's kind of very, very interesting for them.
That's really fascinating on a number of levels. We did a podcast earlier with a lady we had met at IAC in Paris. She looked and she explained in a childlike way to help us was, if you're remote sensing and taking images of the Earth and every day you pass over, you don't need to send every pixel. You need to send the pixels that have changed. And that way, once you have the original photo, it's only what has changed. And that was a way to save data, zeros and ones. Yeah. Everything I think of is zeros and ones. We need to get more info from fewer zeros and ones coming downstream. Is that a fair way to summarize what you said?
That is. And now I'm going to say something controversial. It would also be not only zeros and ones, it could also be zeros and ones at the same time. That's the quantum bit. So you can encode much more information on that, and it's much faster but it's still, all this stuff, this quantum stuff is still in the early days. So this is just a demonstrator that we flew. And so my point was, it would be much more faster for computationally larger data sets and it would be, it can encode much more information than just zeros and ones, the classical bits. The CubeSat that we had like several use cases on board to demonstrate this. So we had a few cameras, like you just said, Earth observation cameras, and these cameras were pointed to the ground. So our use case was to find dams over South Dakota, like large structures that hold back large bodies of water. And our machine learning would find it and then just point it out with a little hitbox. And then if it found a dam, this hitbox would then be cut out and then fed to a quantum algorithm on board. And that would say, yeah, I agree with you, or no, I don't agree with you. And if we found a dam, and the quantum machine learning would confirm that, win, mission success. And then we would also only transfer down this hitbox, basically. So therefore, that was demonstrating that this second goal of us was correct. And that was one case. The second one was to identify atmospheric gravity waves. So those are not the gravitational waves. Those are those, if you look at the clouds, sometimes you see clouds that look like these wave patterns. If you throw a rock into a pond, sometimes you see those ripple effects. Mm-hmm. So those clouds look like that. These are atmospheric gravity waves. They are just very rapid hot and cold air exchanges, but they're a nuisance for air traffic. And that's why NASA is interested in that.
So it's you're quantizing convection and turbulence, potentially turbulent sections of the atmosphere?
We didn't personally quantify it. I would say there's maybe research scientists that work directly in that field that may do that, but I'm not familiar with that. We just looked at those clouds, those materializing visual effects in a visual way, and looked at the images where we could see those cloud patterns. And now again, machine learning and QML would just look at the whole picture, and then there's one, and then do the same thing again as with the dams, basically. So we just used the image data.
This is fantastic. So many things to think about, but I have one last question for you.
Sure.
What is your next mission to space, if you're currently working on one, or what would you like your next mission to space to carry, or what that you built with your own hands would you like to see fly next?
Wow, that's it's a hard one. So on one side, maybe I split it in two. On one side, I would like, so this tech demonstrator that I just mentioned, that was to demonstrate that this CubeSat can be done with a high altitude balloon. So that was a high altitude balloon flight. So the next natural phase there would be to send it up into orbit on an actual CubeSat as a delivery mechanism. But the second half would be going back to GeneLab. So we used some experiments on board the satellite with biological data as well, and GeneLab is very interested in utilizing those algorithms in AI and QML now as well. So we're thinking of producing perhaps a container for research that encompasses everything, like for models, analysis, like a self-driving, I would say perhaps you could call it a self-driving lab, more or less. So that you could utilize on the ISS and run some studies with a set of machine learning and on board that you could then use for monitoring, let's say if it's plants in space or if it's something else in space, something like that. Perhaps.
Fantastic. This has been great, Frank. I wish, you talk about 5 hours, but we're just going to have you come back.
I think I was just going to say,
be happy to.
I can think of several of the students in your wolf pack who are really up this alley. And that would have been like my final question to you, if you don't mind me throwing one more in, is for our students who are definitely interested in computer science, programming, AI, machine learning, all of that. What should they be thinking about as they're developing their skills now? And even where you see AI going even, quickly in the future. So what are the skills that they need to be working on?
Okay. I'm going to say something tricky here. So in general, I would say the main skill that you would need to have is curiosity and interest. So just driving curiosity and the interest of finding out how the world works, basically, and then everything else will come with naturally. Where the field is going, that's the point where I want to mention something interesting here, because I'm seeing this in computer science, for example. So let's say you have with all the new AI and machine learning things coming around, right? So we have something called software engineering underneath, let's say, computer science, if you allow me to put it under that umbrella. And we also hear all these fears currently because of so many new machine learning models that, oh, we may be out of our jobs, or what should we do here and there because everything gets automated. I think that the future is perhaps a little bit more positive than that, because yes, the software engineer, as an example, may disappear over time, but new things may come up. So it may fuse with AI actually. So to tell you about this, you can now tell language models, you can tell it, hey, write me an Xcode app that does something, and it will give you the Xcode. This is the development platform that iPhone or iOS uses, or Apple devices. So then you can copy paste it on your iPhone and it runs. You have an app, great. And then you can tell it, I don't like this window, make it blue, or make the button bigger and move it over there. And it will do it. You can copy paste it again. You have an. Where I'm going is software engineer may not be called software engineer anymore. It may be called software designer in the future, because it has this creative aspect involved where the AI takes the labor of all the coding behind the screen, but you can just tell it what you want, and therefore it can be much faster. And who knows where this is going?
Right. So while one tool may displace one type of worker, that tool becomes then useful for a new type of
a more creative one who has the freedom to be able to explore it.
Yeah, you often wonder, you hear jokes about the guy that did the best horseshoes, when the first cars came out. He was out of a job, but we all benefited from the cars, at least, so to say. Frank, we really appreciate your time today. I've enjoyed it thoroughly.
Pleasure.
We're going to, when we end the recording, I'd love to ask you just a couple of quick questions. Thank you so much, Frank. And again, on behalf of our Small Set Education Conference, Kevin Johnson and I are very grateful for your contributions and your support on our committee. And we hope you can make it this year to Florida in October.
Thank you very much. Yeah.